Trigonometry then is another topic that involves right-angled triangles. However, this one is to do with both sides and angles, using one to work out the other. You may also know this by the name or the acronym SOHCAHTOA, which, if you're not familiar with it, or if you need reminding, I'll go over the definition of in a second. First of all, though, if we were just to look at an example of a right-angled triangle, we've got our three sides and an angle we're going to measure. The angle you may see denoted as x, but it may also be seen as theta, which just looks like this, just in case x is being used for something else in the question. And then as for the sides themselves, the longest side, the side that is opposite the right angle, we're going to call the hypotenuse. Always has to be the hypotenuse. So you could just represent this with a h. The other side that then touches the angle, whichever angle it is that you're measuring, it's always going to be either this or this. It's never the right angle itself. The other side, as I say, touching that angle, we're going to call the adjacent, because adjacent as a word just means next to. And you can represent this with an A. And then the other one, which is opposite the angle you're measuring, is O for the opposite. Okay. Now, in these questions, you're either going to have two sides and want the angle, or know a side and an angle and want the other side. If you knew two sides and wanted the third, you could just use Pythagoras. If you knew two angles and wanted the third angle, you can just say that angles in a triangle add up to 180. This is where then we come to the functions that are going to make up our trigonometry, the sine, cos, and tan. Now for sine, you can work this out. The sine of whatever angle you're measuring is the opposite divided by the hypotenuse. Cos is the adjacent divided by the hypotenuse, and tan is the opposite divided by the adjacent. This is where we get this acronym then for sine, opposite hypotenuse, SO, cos, adjacent to hypotenuse, CA, and tan, opposite and adjacent, TOA. So it just tells you, given on which sides either you both have or you have one and want the other, which function we're going to be using. With this in mind then, let's provide ourselves with another right-angled triangle, and this time just label some sides, some angles. So let's say that this angle here is 50, that this side here is 10, and we're after the hypotenuse here. Well, the two sides that are involved in this question are, as I say, the opposite and hypotenuse. So we're going to be using sine. The sine of the angle 50 equals this 10 over the unknown hypotenuse. Well, in order to make this hypotenuse a subject, in order to work it out, we're going to have to get it out of the denominator. In order to do this, we're just thinking about how we rearrange formulas. We're going to times it up onto this side. So our unknown is now times by the sine 50 to give 10. And then just to get this on its own, we'll have to divide the sine 50 again. So it's 10 over sine 50. In other words, if the thing you're looking for is in the denominator here, you can just switch it with whatever's after the equal sign. And just at this point, you would plug 10 over sine 50 into your calculator, and that's going to give you that it's approximately 13 in length. Again, if we're rounding to the nearest whole number or to the nearest however many significant figures in this case, it's 13.05. So actually, yes, we could call this 13.1 if we wished. Well, let's then try another example. If we were just to draw ourselves another right-angled triangle, and this time let's say we know the hypotenuse. We know the hypotenuse is 7. Let's call the angle 40 this time, and we're going to be after, instead, the adjacent. Well, the two sides involved in this triangle, as I say, the adjacent and the hypotenuse, that's going to lead us to use cos. So the cos of 40 is going to equal our unknown adjacent over 7. Now for the rearranging, we're going to bring this 7 up onto this side so that our unknown is no longer being divided by it. So this gives us 7 cos 40. And again, you just put this in your calculator, and that's going to give you, so let's say 2 decimal places this time, an answer of 5.36, which again will be this length here. For one other example though, before we move on, let's actually see what happens if we don't know what the angle is, but we know everything else. So a right angle triangle could also look to be this way up. Again, just making clear our right angle is here, and the angle we're after is going to be here. Now, let's say that this length here is going to be 12, and this length here is going to be 17. The two sides that we have labelled here are going to be the opposite and the adjacent compared to the angle here. This diagonal here is our hypotenuse, it is the one we're not using, so we're going to ignore any function that involves that one. To start off with then, you would simply say that tan of whatever your unknown angle is going to be as 12 over 17, the opposite over the adjacent. But now, in order to get this angle on its own, again, with any kind of rearranging, the thing you're looking for, you need to get it on its own, not connected to anything else. So we need to get rid of this tan. What you can do is say this unknown, which again, you could have labelled as x or theta or anything like that. We're now going to say it's tan inverse, tan to the minus 1. You'll find this by doing shift and then that same trigonometric function button. And then you put this fraction on the inside here. And once you've done that, that gives you an angle of approximately 35.2 degrees. Alright, let's just see if you can now do a question on your own. If just down here were to draw one more right angle triangle, we're going to label the corner. We're going to say this corner here is going to be 70 degrees. And that the hypotenuse here is going to have a length of 4. What then is going to be the length of your opposite? If you want to pause the video, just have a go at this on your own, and then restart when you're ready, and we'll see how you did. Okay. Well, because the two sides involved in this question are the opposite and the hypotenuse, once again, we'll be going back to using sine. So sine of 70 should equal our unknown opposite over the hypotenuse we know of 4. For the rearranging, we'll just move this 4 up here by timesing it so that we're left with the unknown on its own. So 4 sine of 70, and that gives you an answer of approximately 3.76 if it was round to 2 decimal places. Okay, well, now that we've covered the main principles of trigonometry at this stage, let's move on to an actual example of a question. As we can see here, it's slightly more complicated than what we've been dealing with, but it's still just made up of these right angle triangles with some angles and some sides. So it's still just going to be working on what we've been doing thus far. What the question tells us is that the ABCD is a rectangle and that CDE is a straight line. AB then has a length of 12, this angle here is 60, and your EAC is 90, again denoted by your square in the corner. And it wants us to find out the length of CE, this long length here on the right-hand side. Well, in order to do this, as we can see, EAC is going to be a right-angle triangle. If we can work out what this angle here is, and let's say what this side here is, we can then work out the total side ECD, or EDC, based on our trigonometric principles. In order to get this angle and the side though, let's first look at the right angle triangle ABC. We have here this 12. This is going to be the opposite because it's the side that's opposite the angle we have measured. And the line AC, which you might want to work out, is going to be your hypotenuse, because it's the diagonal that's opposite the right angle. With this in mind then, if we're dealing with opposite and hypotenuse, once again, we're going to be using sine. So the sine of 60 is going to equal our 12 over this length AC that we want. In order to get AC, as we were doing in the previous examples, it's currently in the denominator. We want to get it out of the denominator. You can bring it up on this other side if we then just bring the sine function underneath. And if we just wanted to work that out in our calculator, we would get a length value of 8√3. So that's what our AC here is going to be. Now you don't need to turn it into a decimal just yet, you might as well just keep it as a surd because this is going to be easy to type in and be accurate. Next comes the angle. Well, because ABCD is a rectangle, this whole angle here is going to be 90. If you've used up 60 here, what does that leave you with? That leaves you with 30. So now we have, for our big triangle, EAC, a side, an angle, and another side that we want. The side that we have, because it's touching the angle, but it's not the long diagonal, that makes it the adjacent. And we're after the hypotenuse. Adjacent and hypotenuse, that's going to be cos. So the cos of 30 is going to equal the adjacent that we know, the 8√3, over the EC or CE, it doesn't really matter which way around you write it. Once again, the thing we're looking for is in the denominator, so we'll just switch the places. So your EC is going to be the 8√3 over cos 30. Once again, we can just put this into our calculators, and that's going to give you a value of 16, exactly 16 centimeters.